right, another energy problem for you. So this is a step up, so it's a little bit harder. I would still call this a pretty easy problem. A 1.8 kilogram block slides on a rough horizontal surface. The block hits a spring with a speed of 2 meters per second and compresses at a distance of 11 centimeters before coming to rest. If the coefficient of kinetic friction between the block and the surface is 0.56, what is the spring constant of the spring? Sounds complex. Draw a picture. So we have a block and it's a rough surface, so there's friction. And it is moving, and it's going to encounter a spring. And then it compresses the spring, there we go, a certain distance before it comes to stop. So we have some initial velocity. It is at rest when the spring is fully compressed there. Okay, what do we know? The mass of the block is 1.8 kilograms. The initial speed when it hits the spring is 2.0 meters per second. So I need to be careful. So that initial speed is when it hits the spring. All right, and it compresses it a distance of 11 centimeters. So the spring compresses 11 centimeters, and right away I want to convert that to meters. Coefficient of kinetic friction is 0.56. We want to know, what is the spring constant of the spring? So what is K? We'll go. Okay. Let's go through. We have our initial, let's see, orange. My initial situation is right there. My final situation is right there. Okay. And now I have forces to deal with. I'm dealing with friction, which means I'm going to have work, which means I need to do a force diagram. So I need to do the force diagram for the forces on the block. So what's acting on the block as it's moving and compressing the spring? Well, we know the earth is pulling down. We know the surface is pushing up. Okay, it's moving this way on a friction-y surface, if that's a word. So friction is opposing the motion, going backwards. And then what else is acting on the box? The spring. The spring is pushing backwards on it too. All right, anything else acting on it? Nope, that's it. All right, then, since it's a work energy problem, I'm going to remind myself that the direction of motion is that way. All right, next up, we do the work energy, or the conservation of energy equation. So initial energy plus minus work equals final energy. Initial energy, is something moving? Yes, we have kinetic energy. Is something above its lowest point? Well, I'm going to just set this to be the origin, that surface. No, it's not above its lowest point. Is a spring compressed or extended? At this moment, nope. So the only energy we have is kinetic, just movement energy. Final energy, is something moving? Nope. Is it above its lowest point? No. Is the spring compressed? Yes. We have spring energy. What does work? All right, so now we have to go back in here and say, what does work in this case? I look at my force diagram, and I say the direction of motion is here. Only forces that have a component in this direction are going to do work. So normal force, no. Weight, no. Friction, heck yeah. Spring, heck yeah. Okay. And they're both opposite, so negative. So we have negative work done by friction. And then, remember how I told you that you have to be careful never to do the work done by gravity? Because we took that into account? The work done by the spring is already taken into account right here. So we don't want a work done by the spring, because we took into account that right here. So just like there's never work done by gravity, there's never work done by spring, because we already accounted for it. So we actually have just three terms. Kinetic energy to start with, friction, taking energy away, and we end with stored energy in the spring. What are you looking for? Spring constant. Okay, so that's going to be in this term. Kinetic energy is 1/2 mv squared, and that's initial. Work done by friction. Okay, so that's the friction force times the distance equals PE spring, 1/2 K compression squared. All right, we want to know, hey, do we know this compression? Yes. Do we know the distance? Yes, because that's the same as the compression. Do we know friction? Careful. We know the coefficient of friction. We don't know the friction force, okay? V initial we know, mass we know. We need to figure out what the friction force is. Well, now we're just going to go back to doing the force analysis, just like we did many, many times with force problems. We know that friction is mu n, and what is the normal force in this case? Well, this block isn't moving up and down, so the normal force is exactly equal to the weight. So the friction force is mu times mg, which means my equation looks like this, minus mu mg. Now here's another common mistake, along with forgetting that squared. Another common mistake is losing track of this distance right here. Equals 1/2 K delta x squared. We now know everything except the spring constant. We can solve for the spring constant. And if you do that, what do you get? I got 415 newtons per meter, which is a pretty good size spring. Pretty good stiffness, I should say. Now, a couple things to just, again, be careful of. You never have work done by gravity. You never have work done by a spring, so you don't have this term right here. And keep that in mind. It's 1/2 mv squared. Square that number. And with friction, don't assume that the normal is always equal to the weight. It was in this case, but you can't assume it always is, just like with all those force problems we did. So you have to look at your force diagram every time to see if it is equal to the weight in this problem. Sometimes it'll be mg cosine theta. Sometimes it's just mg. So you just gotta be careful with that. And then, even though we have these two different symbols, d and delta x, in this case, they're the same thing. The compression of the spring, how much the spring was compressed, is the same as the distance the box traveled while pushing the spring, compressing the spring. So don't be fooled that these are two different things. They're really the same thing. All right, anything else? Is it reasonable? Yeah, it's pretty reasonable. It's a nice heavy box. Not too fast, but that's pretty good. It's not your slinky, but that's a pretty good size spring. I think that's a reasonable answer. Okay, that is an example of kind of an easier work energy problem, conservation of energy problem, involving a lot of different pieces, and just a reminder that no work done by gravity, no work done by spring, and hopefully this is all making sense to you. Bye.